We present a new method for denoising optical coherent tomography images, also known as OCT images. The proposed method is called Geodesic Denoising. The medical OCT denoising deals with removing speckled background noises on the one hand and retaining pathological structure on the other hand. OCT provides in vivo cross-sectional three-dimensional images of the retina on micrometer resolutions. A cross-sectional image from OCT is called B-scan. OCT images reveal the layer and pathological structure which are clinically important for ophthalmologists. Here we see the healthy retina B-scan. The unhealthy retina B-scan is shown here. The highlighted cysts are clinically important because they are a very common feature for retinal diseases like non-vascular AMD and macular edema. The poor quality of OCT images hides image features that are important for diagnosis and influences the accuracy of segmentation and pattern recognition algorithms. The proposed geodesic denoising is patch-based method. It uses a global searching and a two-stage denoising to find the best similar patches for noisy samples. The similarity of patches is computed based on geodesic pattern that preserve structural information during denoising. Here we quantitatively compare the performance of different denoising methods. The original noisy OCT images and geodesic denoised one is shown here. Almost all the background noises are removed, while the cyst structure are retained as highlighted with arrows. In comparison with other 3D denoising methods, the cysts are more denoised and their structure is retained by geodesic denoising, while the BM40 fails to remove background noises and the cysts are still noisy, especially for highlighted ones. The diffusion method suffers from blurring effects that makes the details smooth, like cyst boundaries as highlighted here. In the next example, we can see the effectiveness of the proposed methods in removing noises and retaining cyst structures. Even the highly noisy cysts are clearly denoised as pointed with yellow arrows. BM40 fails also in these cases when it is compared with the proposed methods. The layer textures and cyst boundaries are smoothed by 3D version of the diffusion method. In this example, the geodesic denoised cysts have sharp boundaries and high distinctions. The distinction of denoised cysts by BM40 is low and their boundaries is not as clear as geodesic one. The cyst structure and distinctions is diminished by 3D version of diffusion methods. For further qualitative evaluations, the proposed method is compared with other 2D denoising methods. The noisy and denoised B-scan are shown here. Boundary structures of a small cyst with low contrast and high noises are retained in geodesic denoising, as highlighted with yellow arrows. The low contrast layers pointed by blue arrows are also retained. The retina texture is smooth in non-local means denoising, and the boundary of cysts are blurred. The low contrast layer pointed by blue arrows is also lost. The total variation fails to reduce background noises, and the distinctions of highlighted cysts are not good. The background noises is still there in 2D diffusion methods. It suffers from blurring effect, but not as much as the 3D one.